Hi, I'm Dr. Robin, aka Double O Pi. This video is the second of what will probably be a 5-video series on metal-ligand complexes. In this video, I'm going to answer 4 common questions on complex formation and give you an idea about what equilibrium looks like for complexes. If you haven't watched the first video, please go back and do that. I'll drop a link in the description below. But first, a quick review of what we covered in the first video. We used cobalt hydroxide complexes as our model in the first video, and I'm going to continue doing that here. A metal-ligand complex forms when a metal, a Lewis acid or electron acceptor, and a ligand, an electron donor, form a covalent bond. This is a reversible reaction, and therefore the free metal ion and ligand exist in equilibrium with the complex. You may remember that in the first video I showed you that a single metal or essential atom can complex more than one ligand. Well, each of these possible complexes has their own formation equilibrium. We'll get into that in a little more detail later in this video and then in gory detail in the 2 videos that follow. One of the questions I'm asked a lot is, for a given metal and ligand pair, how do I know whether a complex will form? There are 2 answers to this question. The first is complicated. If you really want to know, go ask an inorganic chemist about hard, soft, acid, base theory. The second is a little easier. That involves the use of a table of complexation constants. More on that in a moment. The other question you might ask is, if a metal and a ligand do react, how many possible complexes might form? That is also a difficult question to ask from a theoretical point of view. It depends on the size of the ligand, the size of the metal atom, and a few other things. Again, it's easiest to answer this by looking at a table of complex formation constants. Frequently, tables of complex formation constants are sorted first by ligand and then by metal. Here you can see a table for the formation of hydroxide complexes. This is just a portion of the whole table. Almost all metals form hydroxide complexes, but it gives you an idea of what these tables look like. After finding a table for the appropriate ligand, you can scan down to find the metal you're interested in. For example, if you were interested in calcium hydroxide complexes, you'd look for calcium, and all of the associated information would be in that row. If you're interested in cobalt 2+, you would look at this row here. At the top of the table, you will see notations for which equilibrium constants you're talking about. We haven't really talked about those equilibrium constants yet and how to use them, so for now, understand that the subscripted numbers correspond to the number of ligands that are being attached to the essential atom. So this refers to the equilibrium constant for essential atom with 1 ligand. This refers to the equilibrium constant for an equilibrium with 2 ligands, 3 ligands, and 4 ligands. Looking back at the table for our row with calcium, we see that there's an equilibrium constant listed for calcium with 1 ligand, but no values for calcium with 2, 3, or 4 ligands. This tells us that the only complex that will form is calcium with 1 hydroxide. By contrast, if you look at the cobalt +2 row, you see 4 values. This tells us that 4 different complexes will form. 1 with 1 hydroxide, 1 with 2 hydroxides, 1 with 3 hydroxides, and 1 with 4 hydroxides. So you probably noticed that each of the cobalt hydroxide complexes I showed you earlier had a different charge. Which leads me to another common question that I often get from students. How can I determine what charge a particular metal-ligand complex will have? The way to find the charge on a complex is to add up the charges of every single component that makes up that complex. For example, in the case of a complex that consists of 1 hydroxide ligand and essential atom that is cobalt 2+, the charge on the complex would be -1 from the hydroxide, and it's a +2 from the cobalt. So the overall charge on the complex would be +1. For a complex made up of a cobalt and 2 hydroxides, you can find the charge the same way, remembering that you have an extra hydroxide, so our charge should be 0. This works great if you've already drawn a picture to help you visualize the complex, but the way I usually do the math is to start with a charge on the essential atom, multiply the charge on the ligand by the number of ligands, and then add those numbers. Doing the math tells us that a cobalt hydroxide complex with 3 hydroxides should have a charge of -1, and a cobalt hydroxide complex with 4 hydroxides should have a charge of -2. Now, I mentioned earlier that any reaction between our metal, which is a Lewis acid, and our ligand, the Lewis base, is reversible. As such, we need to think of complex formation reactions as equilibria. In the first video, I talked about how the reaction mechanism for the formation of a cobalt hydroxide complex with two ligands does not occur with both ligands bonding to the cobalt at the same time. Instead, you have a stepwise reaction where first one hydroxide reacts with the cobalt to form this complex, then the other hydroxide binds to form the complex with two hydroxides. Here are the two stepwise reactions involved in forming the cobalt hydroxide complex with two ligands. Each has its own associated equilibrium constant. There are many types of equilibrium constants that use the symbol K. We're going to add a subscript of F to indicate that it is a complex formation constant. Let's think for a moment about what equilibrium would look like if we didn't look at the separate steps of the reaction. This would be the equation for that reaction, so the equilibrium constant would look like this. As you can imagine, we don't want to use the notation K sub F to describe this because it's not a stepwise formation constant. Instead, we're going to use the symbol beta. And we're going to add the subscript 2 because we want to show that this is the equilibrium constant for the cobalt hydroxide complex with two hydroxides. So when you're calculating equilibrium concentrations of metal-ligand complexes, you need to pick which sort of equilibrium constant you're going to use. You can use K sub F values if you want to use stepwise equilibrium constants, or you can choose beta values if you want to look at overall reactions for each complex formed. So which one should you choose? Whichever one is more convenient. That is, whichever one you actually have a table for. Before we get into the summary, if you found this video helpful, please take a moment to click all of the things to engage with the YouTube algorithm. And now let's think back to what we've talked about in this video. First, if you're wondering whether a particular ligand will bond with a specific metal, or how many possible complexes it might form with a metal, check out a table of complex formation constants. To find the charge on a complex, add up the charges of each individual component. And finally, for complexes with more than one ligand, we can either think of the formation equilibrium stepwise, in which case we will use the complex formation constant K sub F for each step, or else we think of it as the equilibrium for the overall reaction, in which case we use the beta constants. We'll talk more about how to use betas in the next video, and a video on the stepwise formation constants, the K sub Fs, will follow that. Hey, thanks for watching. I'm looking forward to seeing you again on the channel soon. Dr. Robin, signing out.